Hello again, AP Physics students. In today's lesson, we're going to wrap up the unit of study on electrical circuits, content-wise anyways. There'll still be a lab to follow after the completion of this lesson. And we're going to do so by talking about what's involved in a capacitor discharging. So up until this point, we've looked at the transition phase in which a capacitor charges. And we also looked at the steady state phase, and the capacitor has reached its maximum charge. And now we're going to look at what happens if you kind of do something to the circuit where the capacitor is then going to discharge from like a maximum value to having no charge at all. And some devices like a defibrillator utilize this idea. So the idea is to like store charge, and then we want to release that charge at a very specific point in time. Okay, so we'll go through the process of how to do that in this lesson. Okay, so let's go back to the circuit that we examined when we were looking at the transitional phase for charging a capacitor. So again, we have a circuit where I have a battery that has an EMF of epsilon, or you can call it V naught. I have a single resistor, which I'm going to call R1, and it has a resistance value of capital R, also a potential difference of V1 across it. You have a capacitor, C2, which has a capacitance of C, and that capacitor has a charge of Q stored on it, and it also has a potential difference of V2 across it. So when you take this switch and you connect it to point A, that's going to result in the capacitor charging. So charge will come out of the positive terminal of the battery. It'll fully charge the capacitor. And when you've reached that steady state, there's actually not going to be any current in this circuit because you only have one possible branch you can go through. Now, if we take that same switch and then after we've charged the capacitor, we then move that switch to point B, what we're then going to do is we're going to take the battery out of the circuit. So if I remove the switch from A and turn it to B, now I have a circuit only on the right-hand side. So the branch that now has the battery is now an incomplete branch. So the battery is no longer part of the circuit. And then what's going to happen is now you just have a branch with the capacitor and the resistor, and this is going to cause the capacitor to discharge. And we'll look through the math of what that's going to be. Okay, so what we're interested in is we want to get a couple of equations. So we want to get charge as a function of time as the capacitor discharges, and we also want to get current as a function of time. So in the process of discharging, we're going to start off with our maximum charge. And the instant you close that switch, the capacitor is going to want to discharge as quickly as possible. So your current is actually going to be really high to start off with. And as the capacitor discharges further and further, the charge in the capacitor is going to lower. And then also the current in the circuit is eventually going to lower to a point where it's equal to zero. Okay, but let's apply the loop rule to just the loop now that no longer has the battery in it. So let's just say that the current through this loop in that bottom branch points towards the right, and we'll call that current I. Just beware that that I is a function of time. It's time dependent. Okay, so if we follow the branch, the current will go to the right, then it'll go up, then it'll go left, and then it'll go down. Okay, that's my loop. Now, to apply Kirchhoff's voltage law to the loop, the sum of the voltages in the loop would be equal to 0. Now, you might be wondering, in order to get net voltage equal to 0, would that not mean that one of the voltage terms would need to be positive here? Because if you have a resistor that has a negative potential difference across it, and a capacitor that has a negative potential difference across it, two negatives would give you a number that is definitely not equal to 0. Now, I think technically speaking, what the capacitor does is the capacitor kind of acts like, I don't want to say acts like a battery, but it definitely drives the discharging process because it's the massive repulsive forces of all the charges on the capacitor that are going to make current, they're going to generate current in the circuit. However, when we write down Kirchhoff's voltage law, we're going to play dumb. And by play dumb, we're just going to assume that we still lose voltage across the capacitor, and then we'll deal with whatever consequence we have of that after we get through the equation. Okay, so let's see what this looks like. So this would be negative V1, which is the voltage drop across the resistor. Subtract V2, which is the voltage drop across the capacitor, is equal to 0. And the voltage drop across the resistor, we can use that format of Ohm's law, is I times R. And then subtract the voltage drop across the capacitor, it'd be Q divided by C. But we're going to substitute in the equation for current. So the equation for current is I is equal to dq dt. And if you plug that into the equation, you then get a differential equation. So you have negative dq dt multiplied by the resistance, capital R, subtract Q over C is equal to 0. And we're going to solve that differential equation to get an equation for charge as a function of time. We'll do that right now. By right now, I mean we'll figure out the initial charge in the circuit first, and then we'll do that. Okay, so let's say that the capacitor has an initial charge of Q subscript I. So that would have been the maximum charge the capacitor would have built to in the charging phase. So it's going to have whatever charge was built up in the charging phase. And that initial charge, when it begins to discharge, we're just going to call it Q subscript I. Okay, so we're going to discharge, which means we're going to take the switch and we're going to close it. So it's connected to point B here. And when the switch is just moved to point B, you're going to have a really, really large current. Okay, because the instant you close that switch, again, all those charges on the capacitor are going to try to repel each other and they want to move away. So that's going to generate a lot of current to start off with because the repulsive force is really, really big. So at your initial point, when the capacitor is discharging, so when time is 0, you would have a charge in the capacitor that's Qi, and you would have a current in the circuit that is I subscript little I. Now, if I look at my equation from the loop rule, negative IR minus Q over C is equal to 0. I'm just going to do a substitution for, I'm going to replace Q with Qi, and I'm going to replace I with I subscript I. And if you do that, you would then have negative I subscript I times R minus Qi over C is equal to 0. And what I'm going to do here is I'm going to just manipulate this equation for the initial current. Because I just want to know what value the initial current is. So if I manipulate that, you would then get your initial current is equal to negative Qi over RC. Now, we need to make sense of what that negative is all about. Okay, so we have, again, that equation for your initial current is negative Qi over RC. What that negative means is that negative is just an indication that when the capacitor is discharging, the direction of current in the discharge phase is actually opposite to what it would have been in the phase when the capacitor is charging. So if we look at the setup of the circuit where the capacitor was charging, so that's when the switch was connected to point A, and then we then have the battery in series, we would see that the conventional current would come out of that long end terminal, and you'd have conventional current moving in a counterclockwise direction through the circuit. Now, when the capacitor is discharging, when you take that switch and you move it to point B, then the direction of current is actually going to be in the reverse direction. So when the capacitor is charging, it was counterclockwise, and then when the capacitor is going to discharge, the direction of current would be opposite. So that's all that negative means there. It's just telling us that the direction of current is actually reversed. But the magnitude of the current, we wouldn't actually need to worry about what that negative sign is. Okay? Just an indication about the direction. Okay, so let's go through the process now of figuring out what the equation is for charge as a function of time. And to do that, we're going to solve that differential equation that I've numbered as equation 2. Now, a big difference here is that when we solve this differential equation, when the capacitor is at a time of 0, so that's just when you've taken this switch and you've moved it to point B, the capacitor actually has a charge. It has the full charge again from the charging phase. Therefore, Q, when time is 0, when we're just starting the discharge phase, is actually going to be equal to Qi. And Qi would be like the maximum charge that was built up in the charging phase. Okay, so let's go to our equation we got from the loop rule. Negative dq over dt times r minus q over c is equal to 0. And then we're going to solve this differential equation using separation of variables. So I'll start off by taking that negative dq over dt times r term and moving it to the other side of the equation to make it positive, in which case you'd have dq over dt times r is equal to negative q over c. To do the separation of variables method, I need to have all the dq and q terms on the same side. I need to have the dt term on the same side. Then I need the dq and the dt to be in the numerator of the equation. So this is actually pretty easy to solve this differential equation in terms of setting it up. So to do this, we're going to have q and dt swapped positions. And it doesn't really matter which side of the equation you put r and c on, because those are both constants, in which case we can just pull them out of the integrals. But just for the sake of like getting to like my simplified equation quicker, I'm going to move r down to the right-hand side of the equation. So then I would have my equation as dq over q is equal to negative dt over rc. Now we're ready to integrate. So to integrate the charge side, we're going to integrate from my initial condition, which is you have a charge of q subscript I. So that's the charge, that the maximum charge the capacitor built to in the charging phase. And then we're going to integrate that to charge at some point later on in time. Okay, so where time is just a variable. The right-hand side of the equation, we're going to integrate from my starting time, which is 0. So we're establishing here that my starting time is just when the capacitor is beginning to discharge. We're going to integrate that to a variable time sometime later, a time t. Okay, so the equation we have here, the left-hand side is in a format 1 over x dx. So the antiderivative of that would fall into the ln format. And the right-hand side, before we integrate, we can pull out what's constant, which is the negative and the RC. So this would then become the left-hand side, ln absolute value of Q, and we're going to evaluate that from Qi to Q of t, and that would be equal to negative 1 over RC, and then the integral from 0 to t of dt. Okay, so to evaluate that, we find the difference of those lns. So we'd have ln of q of t minus ln q of I is equal to negative 1 over rc. And the antiderivative of dt would just be taking the antiderivative of 1 with respect to time, and that would just be t. And we're going to evaluate that from 0 to t. If you have a difference in logarithms, or natural logarithms. Again, a natural logarithm is just a log that has a base of Euler's number e. We can write a difference of logs as a quotient. So the left-hand side of the equation, they can write as ln of q of t over qi is equal to negative 1 over rc t minus 0. Now, to get to qt by itself, I need to get it out of that ln. So to undo the ln, we kind of applied the counterpart of what the ln function is, and that's the exponential function. So what we're going to do is, to get rid of the ln, we're just going to take the exponential function and we're going to raise it to the power of the terms that you see on each side of the equation here. So that would become e to the ln of q of t over qi is equal to e to the negative t over rc. Okay, the e and the lns, they just cancel each other off. So then you'd be left with q of t over qi is equal to e to the negative t over rc. And then to get q of t by itself, move that qi up to the other side, in which case you'd have q of t is equal to qi e to the negative t over RC. If you wanted to, you could take that equation one step further, and you could also write it in terms of the time constant. So again, the time constant is just the product of R times C. And if you did that, you could also write down Q of t is equal to negative QI e to the negative t over tau. And we'll worry about plotting that graph in a moment, but already take note of the fact that this is just an equation that's in the format e to the negative, whatever your variable is, it's e to the negative t. Now, we also want current as a function of time. So again, current as a function of time, we're just going to differentiate that equation for charge. So again, our equation for charge is Q of t is equal to QI e to the negative t over RC. And to figure out current, we're going to find the derivative of Q with respect to t, which means I'm going to find the derivative with respect to time of QI e to the negative t over RC. Before I take the derivative, you can pull out anything that's constant. So the thing you can pull out here is QI, because that initial charge is a constant based on the circuit that we have. So you'd have QI is the derivative with respect to time of e to the negative t over RC. And then we just need to take the derivative of e to the negative t over RC. So that's a derivative in the format, or that's a function in the format e to the ax. And if you look at your formula sheet, the derivative of e to the ax would just be a times e to the ax. You're just applying the chain rule. So the derivative would then be qi multiplied by negative 1 over RC, e to the negative t over RC. Now, we're just going to simplify things a little bit. So then I have I of t is equal to negative qi over RC, e to the negative t over RC. But it turns out that everything in front of Euler's number there, the negative q over RC, I did this little sidestep calculation here, or I shouldn't say calculation, derivation, where I showed that the initial current is actually equal to negative qi over RC. So we can actually replace that in our equation here. Yeah, so little I is equal to negative q over RC. Therefore, if we sub it into the equation, we would have I of t is equal to little I, e to the negative t over RC. And if you want to write this in terms of in terms of the time constant, you could write down I of t would be equal to I of t is little I, the initial current, e to the negative t over tau. So this equation is also in the format e to the negative x, or e to the negative t in this situation. Okay, now we want to just quickly sketch the graphs of what this looks like. Although both these graphs are very intuitive, and they actually both share the exact same shape because they both have that e to the negative t format. So this is what the graphs looked like when we were charging the capacitor. So when the capacitor was charging, my graph for Q as a function of t had that controlled growth, where it had a controlled growth up to a maximum charge, where that maximum charge was just capital C times the EMF of the battery. And then in the process of the capacitor charging, the current started to approach zero, because if the capacitor and the resistor are in series, once the capacitor is charged, there's no longer any current through that branch. So the current started to undergo that exponential decay. So just if you look right here, the format e to the negative t has that exponential decay shape. The format 1 minus e to the negative t has that controlled growth shape. So again, just something to just be aware of, because these are the types of shapes of graph that we end up having to plot the most when it comes to specific questions on the AP exam. Okay, now we want to plot the graphs for Q of t and I of t for the discharge phase. Okay, now for the discharge phase, for charge as a function of time, the equation we got is QI e to the negative t over RC. So that has that e to the negative t format, which is going to be exponential decay. So it has that inverse type shape. Now, if we want to show what the time constant is here, we'll do that in a second. But your initial current here, QI, that's actually what the capacitor, the maximum charge the capacitor would have built to in the charging phase. So whatever Qmax is here, that ends up being the initial charge in the discharge phase. So that's also C times epsilon. In terms of the time constant, the time constant for this equation would represent the time for you to only have 36.8% of the charge remaining on the capacitor. Okay, because the capacitor discharges quite quickly. Current as a function of time also has this shape. So it's I of t is equal to I little I, e to the negative t over RC. So it's also going to have that exponential decay shape. The initial current, we have I subscript I. And then if we want to represent the time constant, so the time constant, again, both these graphs have the exact same format. So the time constant will represent the time required for you to only have 36.8% of the original starting current when the discharge began. Again, as soon as you connect that switch so it goes to point B, the capacitor like badly wants to discharge because of all those repulsive forces. So the current initially is really high, and as the capacitor loses more and more charge, those repulsive forces go down, and eventually the current just drops off as the charge is nothing. Okay, now we're just gonna, before we get into the example, we're just gonna do like one final topic, kind of talking about variations in the time constant. What I mean by that is the charging time and the discharging time can be a little bit different. Sorry about that. I had a cat my cat was just trying to get into a plastic bag and it was distracting me. Okay, so the charging and discharging times are not necessarily always the same. They can be, but it really depends on like how the circuit is actually set up. So I'm going to show an example of a circuit that actually does not have charging and discharging times that are identical. And this is actually going to be the circuit that we're going to look at in the example problem. So what I have is I have a circuit with 3 branches. On the left-hand side, I have a branch with a battery, V0. In the middle branch, you have a capacitor, which we're identifying by C0. And then we have a resistor in that same branch. So that resistor is R1. And then on the right-hand side, you have a resistor, which is R2. Now, depending whether you close that switch or you open that switch, that actually has an effect on what the equivalent resistance in the circuit is going to be. So if we look at this, okay, when you close this switch and the capacitor is charging, R1 and R2, components of these two are actually in parallel with each other, okay, to start off with. So you'd have R1 and R2. This is when we're charging. These guys are components of them are in parallel. Now, if you have resistors that are in parallel, what that does is that causes the equivalent resistance of the circuit to go down. Now, when you actually, so that's when the switch is closed. Now, when the switch is open, we're just going to have the capacitor discharging any loop that kind of is formed between the middle branch and the right-hand side. So in the discharging phase, you would only have, so the battery is now taken out of the circuit. So now you would have R1 and R2 along the same branch. So when you're discharging R1 and R2, these two resistors would then be in series with each other. And if they're in series with each other, what that does is it makes the equivalent resistance of the circuit a little bit bigger. Okay, so if the switch is closed and we're charging, we have the resistors, components of them that are in parallel. And if you open that switch and the capacitor is discharging, then because there's only one branch for the current to move through, they're in series, which has an effect on the equivalent resistance. And if you change the equivalent resistance, you can also change the time constant. So our equation is tau is equal to Req CEq. So in the charging phase, because Req drops because you have resistors in parallel, that actually makes the time constant lower. In the discharge phase, because the equivalent resistance is bigger due to the resistors being in series, that makes Req go up. And if the capacitor is equivalent capacitance is constant, which it is, because we're not changing the capacitor here, that would cause the time constant to go up. So in this case, it would turn out that the time constant for charging, so I could say TC, is actually going to be less than the time required for the capacitor to discharge. So those charging times and discharging times are not the same in this situation anyways. Okay, now we'll come back to this circuit in just a moment here. But basically, when the capacitor is charging, the switch is closed, and that makes R1 and R2 in parallel. If they're in parallel resistors decrease the equivalent resistance of the circuit, which will make the time constant go lower. And when discharging, S is open, and we only have one possible branch or path between the middle branch and the right branch. That puts R1 and R2 in series. And if those two are in series, then that makes the equivalent resistance go up, which causes the time constant go up. So the time for discharging will be bigger than the time for charging. Okay, but let's actually go to an old AP exam question now that it implements this circuit. This is actually a really hard question. I mean, and you can see that based on the score, the average score of 5.29 out of 15. It's very difficult conceptually. The math itself isn't bad. Like there's no differential equations we need to solve, but conceptually, like you've really got to understand like what's going on with the circuit that incorporates capacitors and switches and whatnot. Okay, so it says in the circuit above, you have a battery at the voltage V0 is connected with a capacitor of C0. You have two resistors, R1 and R2. And it doesn't tell me the value of R1 and R2, but it does tell me that R1 is bigger than R2. Okay, we're gonna have to make use of that fact in a little bit. Okay, it says the switch S is open and the capacitor is initially uncharged. Okay, so if it's open initially, there's just nothing going on. Now it says the switch is closed at time equals 0. So what we're doing now is in this first part A, we're going to charge the capacitor. Okay, so as soon as I close this switch, we're going to charge the capacitor. Okay, now, in terms of what the shape of the graph looks like, now we already know what this looks like. If we have a capacitor that's charging, capacitors charge with a controlled growth. So if I want to sketch the shape of this graph here, it would just look something like this. Now, the complication here is that it does say that you must label any intercepts, asymptotes, maxima, and minima with numerical values or algebraic expressions as appropriate. Okay, so what that wants me to do is I need to identify what the horizontal asymptote is at the very top, okay? And we can just quickly sketch what that would look like. So I'll just do it in purple here. So let's just kind of go and say here's the horizontal asymptote. And we'll go all the way across. Best I can. This would be easier if I had a ruler. Okay, so it goes all the way across here. And what I want to do is I want to identify what this Qmax value is equal to. Okay, what is Q max. Okay, so now we kind of have to like start thinking about what's going on in the circuit here, okay, to figure out what Q max is. Now, when you've reached your maximum charge, it means the capacitor is fully charged, okay? So Q max is when this guy would be fully charged. When this capacitor is fully charged, there would actually be no current through this branch. Now, if there's no current through this branch, then this would simply mean that the potential, if there's no current through the resistor, then that would mean that the voltage across resistor 1 would be equal to 0. Okay, because the voltage would be I times R. If there's no current, then there's no voltage drop across here, which means that we're going to have all our voltage lost across the capacitor in this loop. So if you actually like follow this loop, so if we went like just with this one right here. Okay, now I'll start to justify a little bit what I'm thinking. Okay, this is probably more than you need to write though. Again, just bearing in mind if this is an actual AP exam question, you have to work super fast. Okay, so what I'm going to say here is I'm going to say when the capacitor is fully charged, no current moves through that middle branch. The middle branch. Therefore, we already talked about this. The voltage drop across resistor 1 would be equal to 0. So what that means then is if V1 is 0 now, if we go back to the picture and look at our loop rule, you would only have voltage gained across the battery and voltage lost across the capacitor. So that actually tells us that the voltage across the capacitor would just be equal to the battery voltage, and that's because since they are in parallel. Now what we can do is we can figure out an equation for the maximum charge. So my capacitor equation for voltage is delta V is equal to Q over C. And we're going to manipulate that for Q. So we'd have Q is equal to C times delta V. And we would then have your maximum charge would then be the capacitance multiplied by the voltage across the capacitor, so VC. And the voltage across the capacitor, when it's fully charged, is equal to the voltage across the battery. So this would just be Q max would be equal to. Now, I think in the question it uses C naught for the capacitance instead of just C. I don't know why, considering how there's only one capacitor, but whatever. Okay, C naught times V naught. So now what we can do is we can go back to this picture and we can actually write down the maximum charge in terms of variables we can actually see in the question. Okay, you must do this. So C naught times V naught. Okay, so that's my equation for charge as a function of time. Now, the next graph we have to do is we need to do a graph of current as a function of time. And it wants me to do two graphs on the same grid, okay? We want to show the current through resistor 1 as a function of time. and I want to show the current through resistor 2 as a function of time. Okay, let's worry about resistor number 2 first, because this is actually the easier one to deal with. Now, if you look at the setup here, regardless of what's going on in the middle branch, if you look at this outside loop, no matter what's going on in that inside branch, whatever voltage you gain across the capacitor or across the battery, you have to lose it across R2. Because Kirchhoff's voltage law would tell you whatever you gain in this loop, which is V naught, you must lose it. And the only way to lose it is across R2. So what that actually tells you is it tells you, regardless of what's going on in the transitional phase, the battery voltage and the voltage across resistor number 2 are always going to be the same. Okay, so let's clarify that. So I'll say part B here. Okay, R2 is always parallel to V naught. And if two elements are in parallel, it means the voltage must be the same. Therefore, V naught must be equal to VR1. So what we can do now is we can get an equation for what is the current through R1. So we would have V naught would be equal to, so VR1, let's go back to the picture and we'll just call the current that goes through this branch, I'll just refer to it as I2. Okay, so if you use Ohm's law, this would be the voltage drop across resistor 1 would be I2 multiplied by R2. And if you manipulate that equation for I2, you'd have I2 is going to be V naught over R2. Now, the thing about this current value is that that current value through that right branch is always going to be constant. Okay, the reason it's constant is that the battery voltage is a constant. The R2 value is also a constant. We're assuming it's an ohmic resistor. And if these two are constant, that means that I2 must also be a constant. And that's always going to be the case, okay, regardless of what's happening in the middle branch. So if we go back to our picture now and we want to draw what the current through resistor number 2 would be, it's constant, therefore it would just be a horizontal line. It'd be a horizontal line where the current is I2. And in terms of the variables given the question, that would just be V naught divided by R2. Now, R1's more complicated. Okay, so it also wants current as a function of time through R1. Now, what we know is that that current is eventually going to drop to 0 because once the capacitor is fully charged, there's no more current through that branch. But what we need to do is we need to figure out, okay, what's a value for the actual initial current? Okay, what does the initial current start at? And then we can sketch the graph. Because the current, whatever value the current starts on the y-axis, it'll just exponentially decay into having no current whatsoever. Now, the way to think about this is when you just close this switch and current just starts to go through the middle branch, because the capacitor has no charge on it at all, you can actually just view you can actually just completely ignore the capacitor for that initial time, okay, just for that one brief instant once you close the switch, because the capacitor offers absolutely no resistance initially, which means that initially, because the capacitor has no charge on it at all, there's going to be no voltage drop across it. Okay, let's summarize this a little bit. So I'll say, okay, where's my pen? So I'll say when the switch is just closed, the capacitor initially offers no resistance. And because it offers no resistance, we can ignore it just for a moment. So if I go back to my picture, what we would have is we would have current that moves through this branch. We'll call that I1 initial. So I1I. But initially, with there being no charge in the capacitor, V across the capacitor would be 0. So what that means is if you now apply the loop rule, okay, so look at, let's do this in a different color. So if you look at the loop rule through this branch, you'd gain voltage across the battery. You lose nothing across the capacitor because it has no charge, and you would lose all that voltage equivalent to the battery voltage across resistor number 1. So what that means is that initially the battery and resistor 1 are in parallel with each other. Okay, so once again, I'll summarize that point. So say V R1. Oh, sorry, I just realized up here this should have been R2, not R1. That's resistor number 2. Let me just quickly fix that up there. Okay, so then we have VR1 would then be equal to the battery voltage, since they're in parallel, and they're in parallel because they have the same voltage. Okay, so now if we try to get an equation for VR1, we'd have, so we have V naught would be equal to, VR1 would be the current through it initially. So again, let's write down VR1 here. Okay, so this would be V naught is equal to the current through 1. So we'll say I1 little I multiplied by R1. And I want to manipulate for the current. So the current through here would just be I1 little I is equal to V naught divided by R1. Okay, so that's my equation for current. Now, that's what the current's going to start at, but before we can plot this, we need to know, okay, which current is bigger. So when I plot this on the graph, is the initial current through branch, the middle branch, going to be higher than current through the right branch, or is it going to be lower? Now, this is where we have to utilize the fact that it tells us that R1 is bigger than R2. So if you look over here, okay, if R1 is bigger than R2, the only difference between these two current equations is that in this equation up at the top here, you're dividing by R2. In this one here, you're dividing by R1. Now, if R1 is bigger, okay, so it tells us R1 is bigger, what that means is because there's an inverse relationship between current and resistance, that this current would actually be lower in comparison to what I2 would be. So when I draw this on the graph, I need to start this initial current at a value lower than I2, and then we'll make it exponentially decay to 0. So going back here, you can just put it somewhere right here. Okay, we'll call this I1 initial, and that would be equal to V naught over R1. Now that's only going to be true just for this one instant, and then we're going to have the graph exponentially decay to 0. As the capacitor gets more and more charged, the current in that branch is going to drop off progressively. Okay, now we get into the second part of the question. So now it starts to give us numerical values. So it says the battery has a voltage of 1.5 volts. The capacitor has a capacitance of 80 microfarads. resistor 1 has a resistance of 150 ohms, resistor 2 100 ohms. Okay, it says the switch is closed, allowing the capacitor to fully charge. And now we're then going to open it. Okay, so this whole thing about then opening it is now going to allow us to look at the discharge phase. Okay, now it says the time it takes for the capacitor to reach 50% of its maximum charge is delta TC. The time it takes the capacitor to reach 50% of its maximum charge is delta TD, and it wants to know which one's bigger. Does it take, so essentially what it's asking here is it's just saying like, does it take longer for the capacitor to charge or does it take longer for it to discharge? So we can actually do this just by looking at the time constant. I know the time constant is the time it takes for it to get to 63.2% of the charge, but if it takes longer to get to 50% of the maximum charge, then it'll also take longer to get to 63.2% of the maximum charge. So we'll just justify that by looking at the time constant equation. Okay, so whoops. So this is part C here. We'll do it up at the top. Okay, so your time constant equation is tau is equal to your equivalent resistance, Req, times CEQ. And then we can just quickly summarize this. So we can say when the capacitor is charging, and we go back here. When the capacitor is charging and that switch is open, R1 and R2 are parallel. Okay, so we have R1 and R2 are parallel. If these two are parallel, then parallel resistors make the equivalent resistance lower. And if you look at the equation, if the equivalent resistance is lower and the capacitance remains constant, that means that the time constant for charging is going to be lower. Now, when we're in the discharge phase, so going back here, that means the switch is now open. So when these switches are open, there's only a single branch for the current to run through, just this loop on the right-hand side. So that now means that those two are in series. So we'd have R1, R2 in series. And if these two are in series, then this means that series resistors make the equivalent resistance go up. If the equivalent resistance goes up, then the time constant is also going to go up. And then we just relate it to those time variables they gave here. So if you have a lower time constant in charging, it means that that delta TC variable, which is what they give, would be lower. And if the time constant is larger in the discharge phase, then the time would be bigger. Therefore, we can just simply conclude that delta TC, time it takes for you to get 50% of your maximum charge, is less than the time it takes for you to lose 50% of that charge. So delta TC is less than delta TD. Okay, on to part D now. So part D says, calculate the current through the resistor R2 immediately after the switch is opened. Now, to do that, we're going to use the loop rule. Okay, so we can draw the direction of current here. So in the charging phase, conventional current would have come out of the battery V0. It would have gone up, right, and it would have gone down through the capacitor. Now, when the capacitor is discharging, the current's going to go in the reverse direction. Okay, so the reverse direction would look like this. Okay, and we want a value for the initial current, which I'll just call I little I. It'll be the same current through both resistors 1 and through resistor 2. Okay, so we're going to apply the loop rule. So we'll say this is VC. We'll say this is VR1. And we'll say this is VR2. We'll apply the loop rule through that right branch. Okay, so let's apply Kirchhoff's voltage rule. So Kirchhoff's voltage rule would be the sum of the voltage in that loop is equal to 0. Now, again, when you write down the loop rule, you just have to play dumb and assume that like everything has a negative voltage across it, because that's how we've been treating them so far. Although I think, like, again, like theoretically speaking, the voltage across the capacitor is positive because it actually drives the circuit. But again, when we write the loop rule, like I said, just play dumb and write it as negative. So this would then be negative VC minus V2 minus V1 to close the loop, and that's equal to 0. So this would then be negative VC. Subtract the current through resistor 2 would be the initial current, I little I, times R2. Subtract the initial current through the circuit, I little I, times R1, and that's going to be equal to 0. Now, what we can do here is we can factor out that common I little I. So we'd have negative VC, subtract I little I, and then we'd be left with R2 plus R1. That's equal to 0. Okay, so now to get I little I by itself, we just move the VC term over to the other side and divide by what's in brackets. So then you'd have I little I would then be equal to negative VC across the capacitor divided by R2 plus R1. Again, this negative sign here is just telling you that the direction of current is opposite to what it would have been when the capacitor is charging. We don't need to use this in the calculation though, because it's just telling us something about direction. So when we actually calculate the initial current, I little I, it would then be equal to the battery voltage, which they give you as 1.5 volts, and then divide by the sum of the two resistance values. So R2 is 100 ohms plus 150 ohms. And then this is now going to give us an initial current, I little I, would be equal to 0.0060 amps. Or if you want to, you could write it in scientific notation as 6.0 times 10 to the 1, 2, 3, negative third amps, or 6 milliamps, I guess. Okay, so that's my initial current value. Okay, that's part I of D. Now, it also says for part 2, it says, is the current through resistor 2 going to increase, decrease, or be constant after you open that switch? Well, that's pretty obvious. As soon as you open that switch and the capacitor discharges, initially, like, the repulsive force is huge, therefore the current's going to be big. But as the capacitor gets has lower less and less charge stored on it, the current is eventually going to go to 0. Therefore, it's got to decrease. So we can just quickly justify that here. We can say for part 2, we can just simply summarize it by saying the current in R2 will decrease. And the reason being is, as eventually there's going to be nothing to drive the current, because the capacitor is the only thing driving the current in the discharge phase. Eventually, it's not going to have any charge on it. So as there will eventually be nothing to drive the current. All right, so it decreases. Okay, we got one more part here. So it says E, part I, calculate the energy stored in the capacitor immediately after the switch is open. Okay, at least this is easy to calculate. So we have E, part I. So I think the best equation to use for figuring out potential energy stored in a capacitor is the one that says UC is equal to 1/2 C and then delta V squared. So we know the capacitance is, that's no problem. Now delta V just represents, that would have been the maximum voltage across the capacitor after you have that thing fully charged. And we already know what that is. So when the capacitor is fully charged, the voltage across the capacitor is just equal to the voltage across the battery. That's because if you go back here, when the capacitor is fully charged, there's no current through the middle branch, which means that you don't lose any voltage across the resistor. Okay, so then we can just turn this equation into UC would be equal to 1/2. Again, they are using C naught to represent the capacitance times V naught squared. So this would be 1/2. The capacitance value they give you is, I think, what we got here, 80 microfarads. So that'd be 80 times 10 to the negative 6 farads, multiplied by the battery voltage, which is 1.5 volts. And we're going to square that. And then we get UC is equal to 9.0 times 10 to the negative 6 joules. Okay, let's box that. Okay, and then we finally just got one part left here to do. Okay, this is actually this is a tricky question to do. It says calculate the energy dissipated by resistor 1 as the capacitor completely charges. Okay, we're gonna have to use some logic to solve this one. So here's how you should think about this. So whatever energy is stored in the capacitor, as it discharges, this energy is then going to be given to the other two elements in the circuit. So the energy stored in the capacitor is then going to be dissipated both in resistor 1 and it's going to be dissipated in resistor number 2. Okay, so there's going to be some energy given to resistor 1, and there's going to be some energy that's given to resistor number 2. Now, the problem is, well, how much? Like, what's the ratio in terms of how much goes to R1 and how much goes to R2? Now, we can actually very quickly prove this in terms of like what kind of relationship exists between the potential energy in a resistor and the actual resistance value itself. So here's what I'll prove it. So I'm going to say that power is equal to the rate at which your potential energy changes. That's delta U over T. The more practical equation for power we typically use is the one that's I squared times R. And what I'm going to do is I'm just going to focus on this right-hand side of the equation, and I'm going to manipulate for delta U. So if I do that, I would have delta U is equal to I squared times R times T. Now, what I want you to look at is the variation between delta U and between R. And what you can see here is, so this is at one point in time. Okay, we can use this, look at this equation at one instant in time where the current's constant and the time is constant. We would then have delta U is just directly proportional to capital R, which means that the resistance higher, you're going to dissipate more energy in that resistor. So what we can do now is to figure out the amount of energy that's going to be dissipated in resistor number 1. So we'll call that delta U R1. We could actually just create a little ratio rule on the fly. So what I would do is, of the total amount of energy, we can write down, this would be R1 over R equivalent multiplied by UC. Okay, so of like the potential energy stored in the capacitor, this is showing me the ratio which is going to go to R1. Okay, we write down a ratio of R1 over REQ. So this would then be equal to R1 is, I think that's 150 ohms. The equivalent resistance would just be R1 plus R2, so it's going to be 150 plus 100 ohms. Okay, so this is just R1 plus R2. And then we multiply by the capacitance, which, by the way, I think if you actually look at this, I think this gives you like 150 over 250. So if you looked at that actual ratio, I think if you reduce that fraction, 15 over 25, it would just become 3/5, which means 3/5 of that energy is going to resistor 1 and 2/5 is going to resistor number 2, just based on how the resistance values compare. Okay, so we multiply by 9.0 times 10 to the negative 6 joules. And then we get the energy dissipated in resistor number 1 would then be 5.4 times 10 to the negative 6 joules. And then we're finally done this example problem. Like I said, a really, really tough question. Again, like you kind of had to make a ratio rule on the fly here to like figure out the energy dissipated in that resistor, which again, it's kind of intuitive, the rule, but nonetheless, like if you're like really compressed for time, it's kind of hard just to like come up with this stuff like very, very fast. But yeah, this is a good question, a hard question, because again, it really like tests your conceptual understanding of how a circuit actually works. All right, so there are no new questions from assignment number 5 from this lesson. So I've just said make sure to complete the remainder of assignment number 5. However, what's going to be the material to reinforce this is going to be a lab. So that's the RC circuits lab. So what you should do is start on that lab right now, and then we'll finish the lab in the next class. And I'll talk to you then.